Hello everyone, welcome to lesson 3 where we're going to do some more simplifying, but while we do simplifying we're also going to apply this to operations. So you're going to see me doing some adding and subtracting of radicals, some multiplying and dividing radicals, and then we're going to finish off with rationalizing the denominator. This is actually going to take you 2 days to kind of go through this lesson, and I'm going to give you a lot of examples of each type. A lot of examples of adding, subtracting, a lot of examples of multiplying, dividing, and then give you a couple examples on rationalizing so that you can get used to A, simplifying, some more practice with that, and B, getting used to what like terms means with radicals. You know how to add like terms in polynomials. Now we're going to look for like terms in radicals. And the key with this is whenever you're adding and subtracting, you always have to have excuse me, the same radicand and the same index. So it's going to require for you to simplify first, then collect like terms as you go. So let me show you our first example. Example number 1. We're going to work with a cube root of 80 plus the cube root of 270. Now the key is you can't just go and add radicands. It's not that simple. What you always have to do, just like when you're adding polynomials, x's get collected with x's, y's get collected with y's. Well, with radicals, you have to have the same index. We have 3 for the index. That's fine. But for us to go and collect these, what we do is we add coefficients if what's inside the radical sign is the same number. So had it been root or cube root 80 plus cube root 80, done, 2 cube root 80. But since it's not, what we need to do is simplify this. Now remember, with cube roots, we are looking for a perfect cube. Well, when I look at 80, I know there's a perfect cube of 8 in there. So cube root 8 times cube root 10 could be how root 80 simplifies. Plus 270, well, it's got a 27 in there. That's a perfect cube. And then again, times cube root 10. One clue that you can see in here is a lot of our radicals should simplify to give you a similar radical inside the brackets. Notice there's a common radical of cube root 10. So we're going to simplify this, and then we can collect like terms. Well, the cube root of 8 is 2. So this is 2 cube root 10 plus cube root of 27 is 3 cube root 10. Now that they're like terms, we can add coefficients. 2 plus 3 gives us 5 cube root 10. And one thing I want you to get some practice on, because you've done some entering on your calculator of radicals, is punch in the original cube root 80 plus cube root 270, hit enter and get that fancy decimal on your calculator, then punch in 5 times cube root 10. You should get the same answer if you've done it right. If you didn't do it right, then you know you simplified your radicals incorrectly, or you punched into your calculator incorrectly. So there's an example with cubes. Let's look at another example. Example 2. We have cube root, or sorry, not cube root, square root 12 plus square root 18 minus root 27 plus root 8. Again, let's go through and try to simplify these as much as possible. Now we're pulling out perfect squares, and hopefully now that you've done a few lessons on here, those perfect squares are a little faster to find. 4, 9, 16, 25, 36, 49, and so on. So look for those factors. Well, 12 can be written as root 4, root 3. 18 can be written as root 9, root 2, 27, can be written as root 9, root 3. 8 can be written as root 4, root 2. Simplify. Square root of 4 is 2 root 3. Square root of 9 is 3 root 2. Square root of 9 is 3 root 3. Square root of 4, 2 root 2. So the faster you get at the perfect squares, the faster you'll be able to simplify the individual terms. And now it's just a matter of collecting like terms. The root 3's get added to root 3's. The root 2's get added to root 2. So 3 root 2 and 2 root 2 is 5 root 2. 2 root 3 minus root 3 is minus root 3. And again, if you want to start checking to make sure you're okay, punch in the original, punch in the simplified answer, and go from there. They should be equivalent decimals. But this is exact values. Your calculator cannot add radicals. It has to add it as decimals. So if you want to keep exact values, this is how you do it. Alright, let's get to a harder one. Example 3. We're going to look at 3 root 48 minus 4 root 8 plus 4 root 27 minus 2 square root 72. Again, we're going to pull out the perfect squares. Well, 48 has a 16 and 3. 8 has a 4 and a 2 for factors. 27, 9 and 3. And 72 is 36 and 2. So there's all my perfect square factors. Now I'm going to simplify. Square root of 16 is 4. Times 3 will give me 12 root 3. Square root of 4 is 2. Times 4 gives me 8 root 2. Square root of 9 is 3. Times 4 should give me 12 root 3. Square root of 36 is 6. Times 2 will give me 12 root 2. Be very careful at that stage. Remember, it's all multiplication, so the perfect square will work out to a rational number, which you just multiply by whatever the original coefficient was. So we've got 12 root 3 with 12 root 3, 24 root 3. 8 root 2, or negative 8 root 2 minus 12 root 2 is minus 20 root 2. That's about one of the more complicated types. Not only do you have lots of simplifying, but you also have coefficients out front. These are the ones that tend to throw people off. It's really easy to make a mistake in your multiplication, really easy to make a mistake in your simplifying. So be real careful with these type. And the last one, the only thing I could do to make this a little bit more complicated is to bring in some bigger radicals and maybe some fractions. So in example 4, let's look at another cube root one so we can get used to some more perfect cubes. Cube root of 64 over 8 plus 2 times the cube root of 375 minus 2 times the cube root of 54 over 3 and minus 5 times the cube root of 24 over 2. Again, treat this the same way, but now we're looking for perfect cubes. Well, the cube root of 64 is really doesn't have to be simplified because 64 can be written as 4 times 4 times 4. So this can be really written as 4 over 8. Cube root of 375 can really be written as 2 times the cube root of 125, cube root 3. 54 is 27 times 2, so cube root 27, cube root 2, and don't forget to divide it by 3. 24 is 8 times 3, so we'll go cube root 8, cube root 3 over 2. So it looks very complicated, but remember, we're going to simplify this as we go. 4/8 can be written as 1/2. Cube root of 125 is 5 times 2 will give you 10 cube root 3. 27, cube root of 27 is 3 times 2 will give you 6 divided by 3 to give you minus 2 cube root 2. That's a lot of simplifying. Cube root of 27 is 3. Well, 3 divided by 3 is 1, leaving you with 2 cube root 2. Cube root of 8 is 2. Well, that'll divide with the bottom, leaving you with 5 cube root 3. And like I said, a lot of times the students, when they do this, they don't have problems simplifying. It's the multiplication part that they end up making their mistake, which means they know what they're doing in terms of the radical work, but they make simple mistakes in terms of their multiplying and their simplifying steps. Be very careful with that, especially when you get to the complicated answers. And now we look to collect like terms. Well, 1/2 doesn't have a radical, so it's separate. I've got 10 cube root 3 and minus 5 cube root 3 should give you 5 cube root 3 minus 2 cube root 2. There's the final answer in its simplified form. So those 4 examples were all adding and subtracting radicals. Whenever you add or subtract radicals, you have to simplify, get to the same radicand, same number inside the radical sign, have to have the same index. You can't collect cube roots with square roots, just like you can't collect x squareds with x's. All right, so the rules of radicals are very similar to the rules of polynomials. Got to collect like terms. Let's look at 4 multiplication type problems. So example 5, we're now going to practice some multiplying. And we've done a little bit of this in the last lesson, but now we're going to use distributive law and FOIL. So example 5, I'm going to take root 3 times root 6 minus root 12. And there's really 2 ways that you could do this. You could look at simplifying where you can first and then multiply, or you could multiply then simplify after. Again, it doesn't really matter. Sometimes simplifying first to take the big numbers and write them a little smaller is easier for some people. Sometimes they just want to go and get the multiplication done down to single terms and just start simplifying from there. There isn't one method better than the other. I tend to do both, depending on my questions and depending on how easy it is to simplify. So you may see me in one question do all my multiplication, then simplify after, or you may see me simplify at the beginning and then multiply. I look at root 3 and root 6, and they can't be simplified anyway, but root 12 could, and I could write root 12 a different way, then distribute, then simplify again, and get this answer. But I'm going to actually just multiply. This is distributive law. So we know when we multiply radicals, we can just multiply these 2 together. Root 3 times root 6 will give me root 18. root 3 times root 12 will give me root 36. Well, root 18 has a perfect square in it as root 9, root 2. Root 36 is a perfect square. That's 6. Square root of 9 is 3 root 2 minus 6. They are not like terms, so you can't collect them any further. This is considered to be simplest form. So when multiplying radicals, you multiply the radicals inside the sign. You multiply the coefficients, which you'll see me in example 6. Notice there's no coefficients in example 5. Well, example 6, I'll bring a few coefficients in. I'm going to put an example 6 right on the same page here so you can see it written beside. This one I'm going to write 2 root 2 times 3 root 5 minus 4 root 8. And again, if you wanted to, the root of 8 could be simplified further. But in this case, again, all I'm going to do is use my distributive law and multiply coefficients, multiply radicals, and then simplify again. So 2 times 3 will give me 6. Root 2 times root 5 is root 10. So you multiply coefficients, you multiply radicands. 2 times 4 gives me negative 8. Root 2 and root 8 multiplies to root 16. Again, look for perfect squares. Now that you've multiplied, it's just like simplifying with addition and subtraction. Root of 10 does not have a perfect square in. Leave it. Root 16 is a perfect square. That's 4. So you get 6 root 10 minus 8 times 4, which is 32. Again, if you want to keep checking your work, don't forget that you already know how to punch these in. And you could actually just evaluate the very beginning, punch it in on your calculator, punch in your answer. They always should be the same result. I know I've said that a few times, but I always stress it in my classes so that you can constantly check your work as you go. Let's look at a couple binomials in the next two examples, and we'll multiply using FOIL here. So example number 7, we're going to look at root 6 plus root 3 times root 2 minus root 3. So in this case, what you do is you use FOIL. First, outer, inner, last. Just like when we did binomial products in Unit 1, we're going to use the same process for radicals. So root 6 times root 2 gives you root 12. Root 6 times root 3 gives you negative root 18. Root 3 times root 2 gives you plus root 6. Root 3 times negative root 3. Like any radical times itself, you can write it as minus root 9. But what you'll do as you start practicing and doing more of this, anytime I always see a radical multiplied by itself, I always just drop the radical sign. Root 3 times root 3 is just 3. And you'll pick up that tip and simplify as you go. But in the meantime, and while you're still getting some practice on this, get used to the method. Multiply radicands, multiply coefficients. Root 12 has a perfect square in it. Square root 4, square root 3. Root 18 has a perfect square in it. Root 9, root 3. Root of 6 cannot be simplified, and the root of 9 can be simplified to being minus 3. Whoops. Root 18 is not 9 times 3. How about 9 times 2? Almost made a big mistake there. So it's root 4, root 3 to be root 12, root 9, root 2 to be root 18. no perfect squares in the root of 6, and the root of 9 does simplify to be 3. This now turns out to be square root 4, which is 2 root 3, square root 9, which is 3 root 2, plus root 6, minus 3. There are no like terms at this stage. Root 3's and root 2's cannot be collected. Root 6's are not common with anything else. You cannot collect any of these like terms. Let's put example number 8 beside this. And the only thing I'm going to do different is put a few coefficients in here now. So it's going to be 2 root 3 minus 3 root 3 times 2 root 3 minus 4 root 2. Again, you multiply coefficients, you multiply radicands. These are the ones that tend to get little mistakes on. Be very careful. So 2 times 2 will give you 4, and again, you can write that as 4 root 9. 2 times negative 4 gives you negative 8. Root 3 times root 2 is root 6. Negative 3 times 2 gives you minus 6. Root 3 times root 3 gives you root 9, or again, you probably might be simplifying that already. And root 3, 3 times 4 to give you positive 12. Root 3 times root 2 is root 6. Let's collect like terms. Simplify before. The root of 9 can be written as 3, so 4 times 3 is 12. 8 root 6 cannot be simplified. 9 is a perfect square, so it's 6 times 3 to give us negative 18. And 12 root 6 cannot be simplified. So now that we simplified each term, we can collect like terms. 12 minus 18 is negative 6. Negative 8 root 6 plus 12 root 6 could be a positive 4 root 6. Subtract 6. Or the order doesn't matter. You could write that as negative 6 plus 4 root 6. Both those answers are equivalent. This type of example, number 8, tends to be about as bad as it gets. Now, they could put a few bigger numbers in here and a little bit more simplifying, but the process is going to be identical. You know, it's the ones where the coefficients are in front. You have to continually remember, multiply coefficients, multiply radicands, simplify radicands, collect like terms. That's what I'm doing over and over and over again. With the multiplying, that's what I'm doing with the adding and subtracting. Now, what we're going to look at in example 9 are some very special binomials, which we call conjugate. In example 9, when you look at a binomial, just like you had conjugates with polynomials, we can have conjugates with binomials. And what is a conjugate? Well, a conjugate is going to be where you have identical binomials with opposite sides. So example number 9, what we're going to look at here is square root 7 plus root 4 times square root 7 minus root 4. And again, you might be looking at this and saying, well, square root of 4 is a perfect square, and I agree. But what I want you to recognize in example 9 and 10 is that these are similar to that x plus 4, x minus 4 that you did in Unit 1, where you had difference of squares. Well, we know from difference of squares that there's a shortcut with these. You don't have to FOIL it. Now, I will FOIL these two examples for you just to get you practicing with FOIL. But if you recognize conjugates, the trick that I showed you back in Unit 1 is just multiply the firsts and multiply the lasts, because the middle terms will cancel. And I'm going to prove that to you. And the other neat thing about this is in your notes it says the product of a conjugate will always be a rational number. In fact, when you finish the multiplying, you will end up with no radicals in your answer. If you do, you've done something wrong, or you didn't have conjugates. So conjugates are identical binomials with opposite signs. And if we were to apply FOIL, root 7 times root 7 is root 49. Root 7 times 4 gives you negative root 28. 4 times root 7 gives you positive root 28. And root 4 times root 4 gives you negative root 16. Notice this is very similar when we were foiling difference of squares. Those middle terms are equal and opposite. Well, the square root of 49 is 7. The square root of 16 is 4. 7 minus 4 is 3. You will always, always end up with a rational when you multiply by conjugates. You'll see the purpose of this when we get to example number 11. Example number 10, again I'm just going to add some coefficients but do the same thing again. We're going to look at 2 root 6 plus 3 root 2, and it's going to be again 2 root 6 minus 3 root 2. You know, just like when we were looking at your expression and factoring and just instantly recognizing what method of factoring you should use, you should be looking at expanding radicals and instantly recognizing what type you're dealing with. Are these conjugates? And then try to pick up the shortcut right away. I'll FOIL this one for you one more time just to prove it to you. But when you're doing these yourselves to save time, I'd probably just multiply first and multiply last. That's all you need to do. So 2 root 6 and 2 root 6 gives you 4 root 36. Again, I'll show you the FOIL. 2 times 3 gives you negative 6 root 12 plus 6 root 12. And when you multiply the last, you get 9 root 4 minus 9 root 4. Again, those middle terms add to 0. That's why FOIL will never go wrong, but you can save yourself a little bit of work because the square root of 36 is 6 times 4 is 24. Square root of 4 is 2 times 9, which is minus 18. 24 minus 18 is 6. You always get a rational number. Now, why is this important? Well, the last thing that you're doing in your notes is you are rationalizing binomial denominators. Remember, one of the rules in simplifying is to not have a radical in the denominator. Well, if you have a single term, it's easy to multiply top and bottom by that single term. But if you have a binomial, you can't do that. So in example 11 and 12, when you had something that looks like this, 2 over root 3 plus root 2, you can't multiply top and bottom by root 3. Doesn't rationalize this. Remember, you are not allowed to have radicals in the denominator. So the way you get rid of a radical, especially if it's a binomial, is to multiply top and bottom by its conjugate. If it's just a single term, all you did was multiply top and bottom by that single term. Now that it's a binomial, you will multiply top and bottom by the conjugate. And what will it do to the denominator? Well, it'll turn it into a binomial, and then you can expand it to get a rational. So on the top, I'll have 2 times the entire binomial. On the bottom, I'll have a binomial times a binomial. And I'll even start to use the shortcut in example number 11 and 12. I know that multiplying a conjugate just means multiply first and multiply last. On the top, I'm going to use distributive law. It's going to be 2 times each term. And since I'm multiplying top and bottom by the same number, I'm not changing the fraction, I'm changing its form. So 2 times root 3 will give you 2 root 3 2 times root 2 gives you minus 2 root 2. On the bottom, again, I'm just going to multiply first. Root 3 times root 3 is 3. Root 2 times root 2 is 2. And since it's a binomial conjugate, the sign is always negative. So when you simplify this, there are no like terms to collect. There's no dividing out of a common factor. We're left with 2 root 3 minus 2 root 2. Done. So there is a purpose to a conjugate. It's to get the radical or binomial radicals out of your denominator. The rules with simplifying: no fractions in the radical sign, no radicals in the denominator, no perfect squares in your radicands. You always have to get rid of that stuff. And the last example on rationalizing will make it a little bit tougher. Example number 12. It's 2 root 7 plus root 5 over 3 root 7 minus 2 root 5. Alright, so this is about as bad as they get. We need to multiply by the conjugate again. And it's the conjugate of the denominator, not the conjugate of the numerator. And don't forget it's a binomial times the binomial in here. So we're going to multiply by 3 root 7. Conjugate will be plus 2 root 5 to top and bottom. 3 root 7 plus 2 root 5. Now this is a ton of multiplying. Alright, you have FOIL on the top and you have conjugates on the bottom. So there's a lot of work here. Very easy to make a mistake. Well, let's just work with the numerator for now. 2 times 3. Just draw out our FOIL here. So 2 times 3 will give me 6. Root 7 times root 7 will be root 49. 2 times 2 will give me 4. Root 7, root 5 is root 35. Root 5, well, since the coefficient is 1, we'll get 1 times 3 is 3. 5 times 7 to give me root 35. And root 5 times 2 root 5 will give me 2 root 25. On the bottom again, I'm just going to do my shortcut. I know with conjugates, I will get 3 root 7 times 3 root 7, which is 9 root 49. Do the last. 2 times 2 to give me negative 4. Root 5 to be root 25. Now we're just going to do a bunch of simplifying. The root of 49 is a perfect square. That's 7. 6 times 7 is 42. The root of 35 does not have a perfect square in it. So we'll leave that. We also know that the other term has a 3 root 35. Just like you collected like terms when you FOILed in polynomials, you should be able to get some like terms when you FOIL with radicals. So 4 plus 3 will give me 7 root 35. The square root of 25 can be simplified further to be 5 times 2, which is 10. On the bottom, square root of 49 is 7. 9 times 7 is 63. Square root of 25 is 5. 5 times 4 to give you 20. Collect like terms even further. 42 plus 10 is 52 plus 7 root 35 over 63 minus 20, which is 43. There's nothing else that you could simplify here. I cannot divide 43 and 52 and 7 by any common number, so I can't simplify that any further. We're done at this stage. Nothing left to collect, nothing left to simplify. So you're going to get lots of practice in exercise 3.3. There's quite a few questions on adding and subtracting, quite a few questions on just multiplying, either distribute or FOIL, lots of conjugates, and lots of rationalizing the binomials. All the different types all at once. Really identify the type of question you're dealing with, and I'll give you, there's actually 2 days scheduled to do this lesson because it's quite complicated and you need to do every single possible question you can to get radicals down pat. Work on exercise 3.3. Take care, everyone.